Hi, my name is Daniel Johnson, and today I'll be talking about near-field terahertz imaging. This is a method for non-destructive testing of electronics, as well as a method used for counterfeit detection. The material is brought to you by Dr. Navida Sadi, Shenji, and myself. Hope you enjoy. As I mentioned before, my name is Daniel Johnson. As a short introduction about myself, I am a recent graduate from the University of Florida with a bachelor's in electrical engineering. And currently I'm working on my master's in engineering management, and I expect to graduate at the end of 2022. I currently work as a full-time lab engineer at the University of Florida. Our lab, the SCAN lab, is part of FIX, Florida Institute for Cybersecurity, and at FIX we offer different types of technologies that are focused on hardware security and physical assurance of electronics. In fact, you can learn more about these technologies through our MES Center. It's known as the National Microelectronics Security Training Center. And if you just search up the word MES, you should be able to find our website and learn more about the requirements. So as I mentioned before, at FIX, we focus on different types of methods that are used for physical assurance of electronics. And here we actually have 4 listed methods. We have the optical imaging, we have scanning acoustic microscopy, we have X-ray, and we also have terahertz. Now all these methods can be used for failure analysis, but we are also considering the fact that they can be used for counterfeit detection. So these characterization methods, they can detect components such as dyes, interconnects, different layers inside the packaging, and overall help us identify if there's any missing or extra components that are not supposed to be there. So first we have the optical imaging. So optical imaging can be acquired by the use of a camera, microscope, or DSLR with different resolution. With the help of imaging processing, optical imaging can be used to detect surface texture, logos, and scale of the IC. However, optical imaging can only characterize the surface information of an IC, so it is very limited in its contribution to hardware assurance. Second, we have the scanning acoustic microscopy, and this can both characterize surface as well as subsurface information. It's mainly used for failure analysis purposes, and it can identify voids, delaminations, and cracks, and etc. So for hardware assurance, it is able to detect extra bond wires, different lead frames, or different IC shapes. The only downside with scanning acoustic microscopy is that it requires the sample to be submerged into a liquid, usually water, and this can lead to sample damage and inefficiency. Also, there's a strong trade-off that should be noted between the frequency, penetration depth, and the resolution. So this means that penetration through thick, heterogeneous integrated packaging will require it to go through more layers and may have overall a lower resolution. Then we have X-ray. So X-ray is widely used to characterize internals, 2D and 3D structures of the ICs. It can both characterize the subsurface information with the 2D X-ray and then also detect volumetric information with 3D X-ray. And the problem with X-ray is the clear layer segmentations. So especially with heterogeneous integration, there's a lot of thin layers, and with noise from metals such as bond wires, the signals to noise ratio of the X-ray can be affected. So lastly, X-ray cannot also be considered as the end-all be-all total non-destructive detection because the ionization. So X-ray can potentially wipe out the memory information of an IC. So as mentioned before, the optical imaging, scanning acoustic microscopy, and X-ray don't provide that total package. And then finally we have terahertz, right? So terahertz time domain spectrum is a new technology that's being used for package IC characterization, And it can in fact characterize the surface, subsurface, and volumetric information of ICs. And since it's not the most efficient one, it takes several hours to scan a sample, it does provide a contactless, non-destructive method. So we'll be getting into that more here shortly. So just as a recap from the previous slide, there's multiple drawbacks to multiple methods. And as we can see here, the Terahertz imaging is an adequate method that provides surface, subsurface, and volumetric information, which makes it a very attractive, non-destructive, and contactless characterization method. It should be noted that when we refer about these terahertz signals, they usually refer to signals that have a frequency between 0.1 to 10 terahertz, and the terahertz frequencies lay between the electro and optical regions, which carries capability from both domains. And again, the terahertz signal is transparent to semiconductor and most of the polymer materials, which makes it even easier to use for contactless characterization. So here we have a diagram about the Terahertz TDS system setup. Here we start from the femtosecond laser pulse, and this pulse is split by a beam splitter into pump beams, which is the blue line, and probe beams, which is the red line. The ultra-fast pump beams will reach the terahertz emitter, and the optical pulse will be converted into a terahertz pulse. After propagating through the samples, the terahertz pulse will refocus onto the terahertz detector. For the reflection model, here terahertz TDS, the terahertz emitter and detector will be placed on the same side of the samples. The signal will penetrate into the sample and get reflected by the interface of different materials, and this detection will collect the signal amplitude as well as change with time and generate the terahertz spectrum. So all this information will allow characterization both of material properties and structural information of the sample. So as said before, terahertz can be used for material characterization. It in fact detects refractive index differences of the samples. And as one example here, we have polymer materials with different thicknesses, and it can detect the different thicknesses and visualize it for us in different colors here. So in this sample, we also see defects that have been detected, and these defects have been detected due to the differences in the refractive index of the air and the polymer material. So another thing to note is the polymer crystallinity, which will affect the terahertz signal absorption. So this means that the terahertz is able to differentiate this polymer with different fabrication processes and aging. And since this process will overall affect the polymer crystallinity percentage, that means we can possibly use it for the detection of counterfeit samples, aged samples, reused samples, or even maliciously modified samples, which have gone through different material fabrication processes. Back in 2018, the terahertz system was used for counterfeit detection, and in fact, it was able to detect samples with that went under blacktopping, and this was able to help us detect different signals between the authentic and counterfeit samples. So just to show you that it's already been being used as a counterfeit detection method. So furthermore, we have the terahertz being used for structural characterization. So it is a very attractive substitute solution to the SAM and X-ray, mainly due to its non-destructive contactless measurement. Here we can see that in the far-field transmission imaging, we are able to detect the internal structure differences between the authentic and counterfeit samples. However, the image resolution is very low, which is mainly because of the signal diffraction due to the propagation through free space. To eliminate these noises and the blurry images, Point spread function has been used to mimic signal propagation. By deconvoluting the PSF onto the original image, the image resolution can then be dramatically increased and have the potential to be used to characterize the more small-scale elements that exist, that are seen, such as in the heterogeneous integrated packaging. Another way to increase the resolution of the images is by using the near-field detection method. So the near-field detection usually refers to the sub-wavelength detection, which will eliminate the free space diffraction problems. The internal structure is able to detect features such as bond wires. However, it should be noted that the main drawback of the near-field detection has a very slow acquisition time. So from our experience using the system in our lab, it takes 10 or even more hours to raster a scan of a sample and generate a high resolution image. Also, since it's in reflection mode, it is able to characterize the 3D volumetric information of the sample. So based on the equation here shown here, we see that knowing the reflective index and the time delay, the thickness of different layers can be calculated. So finally, we have the terahertz being used to characterize the transistor inside an IC, and this is being done by using the laser terahertz emission microscopy. This method is originally developed to analyze the defects and disconnections inside the large scale IC, and the principle of the system is described here. So we have a inputted terahertz signal from the sample backside. If there's no defects, the metal layer will then act as a terahertz antenna and generate the signals. And if there is a defect inside, there will be no emission of the signal. So as you can see here on the picture on the right, there is a black yellow box that shows that there's no signal being transmitted. This method is also able to differentiate the types of transistors, so p-type and n-type transistors, as well as characterize the carrier concentration and the carrier mobility of the semiconductors. So overall, while this method only provides several microns resolution, it does seem like a promising microscopy that can be developed and achieve a nanometer or even atom level resolution. So as we hinted throughout the slide, some of the characterization information collected by terahertz systems can help us create a unique fingerprint. So these fingerprints can be used for tracking and tracing of samples throughout the supply chain. In fact, we had in mind two different types of examples. We have the external fingerprint and then the inherent terahertz fingerprint. So the external one would consist of a PE tag, which is sprayed by antitrust coating, and this antitrust coating will have different thicknesses and variances that are around 1 millimeter. So with the help of machine learning classification models, tags with different thicknesses can be classified once the measurements have been taken. Then there's the other type that contains that uses the materials contained within the sample and the different layers. So the material differences and the refractive index differences will be detected by the terahertz measurement, and by choosing a certain frequency window, the unique tag can be detected. With this all being said, there are possibly a few drawbacks, such as fabrication variances and the thickness of each layer. So that's just something to keep in mind, but I know that this is a concept that still is in the works. In summary, the terahertz is a unique, relatively new hardware assurance tool. It can provide extractions of internal features as well as characterization of material differences. When all put together, It can create a fingerprint for the sample and ultimately be used throughout the supply chain. With this being said, I appreciate you attending this talk, and hope you take care.